There is a profound mystery hidden just before the very beginning of time. We think we understand the Big Bang, but it leaves a colossal question unanswered. What, if anything, came before it? This journey through 15 mind-bending theories will transform how you see our cosmic origins, giving you a front-row seat to the most daring ideas in theoretical physics. We will explore realities where universes cycle eternally, and others where our entire existence is a holographic projection. By the end, you will possess a deeper appreciation for the fundamental nature of reality itself. How do you picture the moment before everything began? Our current story of the cosmos begins with the Big Bang, a tremendous outward rush of all space, time, and matter. We can trace this expansion backward like a movie in reverse, watching galaxies draw closer together. Yet this cinematic journey reaches a point where the film itself appears to burn. As we rewind to the very first fraction of a second, our equations falter and our understanding shatters. We encounter a singularity, a point of seemingly infinite density and temperature where the known laws of physics simply stop working. It is a cosmic firewall that blocks our view, preventing us from peering any further into the past. The Big Bang theory masterfully describes the universe's evolution from that hot, dense state onward, but it remains silent on what ignited the explosion in the first place. It tells us what happened after the beginning, but not why the beginning began. This fundamental limitation is not a failure of science, but rather a beacon. It illuminates the very edge of our knowledge and challenges us to look beyond. The quest to understand what existed before is not mere philosophical speculation. It is a necessary scientific endeavor, pushing cosmologists to employ the most advanced tools of mathematics and quantum principles to build bridges across that ultimate abyss. Perhaps our cosmos is not a one-time event but a heartbeat in an eternal body. The first theory, the Cyclic Universe, proposes exactly that. It envisions a reality that breathes, expanding for eons until its own gravity pulls everything back together in a cataclysmic event known as the Big Crunch. This is not a final end but a cosmic reset. The universe collapses to an incredibly hot, dense state, and from that furnace, a new Big Bang erupts, starting the cycle all over again. This process repeats forever, with no true beginning and no final end. Our entire history, from the first stars to the rise of civilization, is simply one act in an infinite cosmic play. This idea finds support in the complex mathematics of string theory, which describes our universe as a membrane or brane floating in a higher dimensional space. Some models suggest that collisions between our brane and a neighboring one could provide the immense energy required to trigger each new cycle of expansion, acting as the starter pistol for a new cosmic race. For physicists like Paul Steinhardt, this model is profoundly elegant. It removes the troublesome singularity, that point of infinite density, and replaces it with a transition, a bounce from one cycle to the next. It presents a universe that is eternally self-renewing. So, could everything we see and know be part of an ancient, rhythmic dance of creation and destruction? This leads us to a theory that posits a perfect mirror to our own reality. This idea of a cyclical cosmos takes an even more radical form. Roger Penrose, a Nobel laureate, offers a vision where the end of time is not a destructive crunch but a quiet, geometric reset. His theory, Conformal Cyclic Cosmology, proposes that our universe is merely one eon in an endless chain. Each eon begins with its own Big Bang and expands for trillions of years until every black hole has evaporated and every particle of matter has decayed into pure light. The universe becomes a vast, cold, and empty sea of radiation, stretched to a state of near nothingness. Here is the profound twist. Penrose uses a sophisticated mathematical concept called conformal symmetry to show that this vast, ancient end state is geometrically identical to the hot, dense, microscopic beginning of a new universe. The end of one cycle and the beginning of the next become one and the same point. It is as if the final, faded page of a book is physically the same as the blank first page of the next volume. This means our own Big Bang could have been the graceful transformation of a previous cosmos in its final moments. The theory even offers a potential way to find evidence. Penrose suggests that colossal collisions between supermassive black holes from a prior eon could have left faint, circular imprints in the cosmic microwave background, the faint afterglow of our own universe's birth. What if the sky holds ghostly signatures of a cosmos that died long before our own was born? This challenges us to consider that time itself may not be the fundamental river we believe it to be. Our journey now takes us to a place where the very words beginning and end lose their familiar meaning. Stephen Hawking and James Hartle proposed a universe that is entirely self-contained, a cosmos without an edge in space or a starting moment in time. This is the no-boundary proposal. To grasp this, picture the North Pole on a globe. If you ask what is north of the North Pole, the question itself is meaningless. The North Pole is a boundary of the coordinate system we use for latitude, not a physical cliff at the edge of the world. Hawking and Hartle applied a similar logic to the entirety of reality. They suggested that when we look back toward the Big Bang, the fabric of spacetime smoothly curves into a closed, finite geometry, much like the surface of a sphere. In this model, the singularity vanishes, replaced by a gentle, rounded-off origin. The most mind-bending consequence is for time itself. At these unimaginably small scales, the distinction between time and space blurs. Time begins to behave like just another spatial dimension. This means there is no before the Big Bang, because there was no time for a before to exist. The universe did not explode into being at a point in time. It simply began to be. It emerged from a timeless state through a quantum fluctuation, a spontaneous event governed by the probabilistic laws of quantum mechanics. In this framework, the universe effectively created itself from nothing, because nothing is the timeless, spaceless state from which its geometry smoothly appeared. This idea challenges the very core of our intuition, which is rooted in a linear flow of time. It asks us to trade our image of a cosmic starting pistol for one of a timeless, self-contained bubble. So, if the universe truly came from nothing, what does that nothing actually contain? Our next theory suggests it might be teeming with an infinite number of other universes. There is a cosmic ocean, and our universe is merely a single bubble rising to its surface. This is the breathtaking vision of eternal inflation and the multiverse. It proposes that the vacuum of space itself possesses a strange, repulsive energy that drives a process of exponential expansion, and this process is, for the most part, eternal. Our Big Bang was not the ultimate beginning of everything. Instead, it was a local event, a tiny region within this eternally inflating background where the expansion energy finally decayed, converting itself into the hot soup of particles and radiation that would become our cosmos. Think of a vast, bubbling cauldron of water coming to a boil. The entire pot is the inflating multiverse, and each steam bubble that forms and rises is a separate universe like our own, pinning off with its own unique properties. Pioneered by minds like Alan Guth and Andre Linde, this theory suggests that quantum fluctuations are the engine of creation. In the frenetic sea of eternal inflation, random fluctuations can cause a tiny patch to drop out of the hyper-expansion, triggering its own personal Big Bang. Our entire observable universe is just one such stabilized pocket, while the greater multiverse continues to inflate forever, giving birth to an infinite number of other bubbles. This leads to a staggering implication, the concept of a landscape of universes. Since each bubble forms from a random quantum fluctuation, the fundamental constants of nature, like the strength of gravity or the mass of an electron, could be set differently in each one. In most of these universes, the laws of physics might be utterly inhospitable to life, but in a rare few like ours, the numbers line up just right. This offers a potential explanation for the seemingly perfect fine-tuning we observe, not as proof of design, but as a statistical inevitability across an infinite array of worlds. We just happen to live in one of the bubbles where life became possible. This idea of a cosmos encoded with infinite possibilities finds a strange echo in a theory that suggests our reality is far less substantial than it appears. Our reality may be a magnificent illusion. According to the holographic principle, the three-dimensional world we experience, with its vast galaxies and swirling nebulae, could be a projection from a two-dimensional surface, much like a hologram on a credit card. The information required to describe every star, every planet, and every one of us is not smeared throughout the volume of space, but is instead encoded on its outer boundary like a cosmic film. This radical idea was born from the study of black holes, where physicists discovered that the maximum amount of information a black hole can contain is proportional not to its volume, but to the area of its event horizon. This suggests that information, the fundamental stuff of reality, prefers to live on surfaces. Visionaries like Leonard Susskind and Juan Maldacena have extended this principle to the cosmos itself. In this framework, our universe could have begun in a purely holographic state, a timeless, spaceless domain of pure information. The Big Bang, then, was not an explosion in a void, but the moment this information was decoded. It was the instant the projector was switched on, transforming a flat, information-rich surface into the rich, three-dimensional theater we now inhabit. Time and space as we know them would not be fundamental, but emergent properties that crystallized from a more basic, information-based reality. If this is true, then the deepest questions about what existed before the Big Bang must be asked not in terms of time, but in terms of information. What was on the cosmic hard drive before it booted up? This leads us to a theory that reimagines the Big Bang not as a beginning, but as a rebound from a prior cosmic collapse, a great bounce. Our universe might not have been born from nothing, but from the death of another. The Big Bounce theory paints a picture of a cosmic rubber ball, compressed by gravity into an unimaginably dense point, only to rebound in the explosive expansion we call the Big Bang. This is not a one-time creation story, but a cycle of collapse and rebirth. Before our universe began its outward rush, it was in its final act of an inward collapse, a previous cosmos contracting under its own immense gravitational pull. Everything we see, every galaxy and star, would be the recycled material of a prior universe that had reached its limit and turned in on itself. The crucial element that prevents this collapse from ending in a meaningless singularity is quantum physics. According to theories like loop quantum gravity, when matter and energy are squeezed to such extreme densities, the force of gravity does not remain attractive. Instead, it flips, becoming a powerful repulsive force. This quantum pressure acts like an impenetrable cosmic spring, halting the collapse just short of infinite density and launching the universe back into a new phase of expansion. This bounce is not a violent, chaotic smash, but a smooth, deterministic transition governed by quantum laws. Physicists like Martin Bojold have developed mathematical models that allow us to trace a continuous timeline through this event, connecting the pre-bounce universe to our own. In this framework, the Big Bang was not a beginning of time but a turning point, a moment of cosmic renewal. The universe's history becomes an endless, rhythmic series of rebounds, each cycle potentially lasting trillions of years. Could everything we know be part of an eternal, breathing entity? This vision of a mirrored cosmos leads us to a theory that suggests our universe was born with a perfect and hidden twin. A perfect cosmic symmetry might have been broken at the dawn of time. The seventh theory, the Dirac-Milne Universe, dares to reimagine one of physics' most stubborn puzzles, the mysterious dominance of matter over antimatter. In our standard model, for every particle of matter created, an equal particle of antimatter should have been born. If that were true, they would have instantly annihilated each other in a flash of energy, leaving behind a cosmos filled with light and nothing else. The fact that we exist in a universe made of matter is one of its greatest unsolved mysteries. This model proposes a radical solution. What if antimatter did not vanish but is still here, simply behaving in a way we have never detected? It suggests that antimatter possesses a property known as negative gravitational mass. This means that instead of being attracted to matter by gravity, it would be repelled by it. Picture trying to push the same poles of two powerful magnets together. That relentless pushing force is how matter and antimatter would interact gravitationally in this model. Before our Big Bang, the cosmos could have been in a steady, eternal state, a diffuse and balanced soup where these repulsive forces kept matter and antimatter largely separated. Our Big Bang, then, was not the absolute beginning, but a dramatic phase transition within this older cosmos. A shift in the fundamental fields may have broken the symmetry, allowing matter to begin dominating and initiating the expansion history we observe today. This theory elegantly sidesteps the need for a singularity, suggesting a continuous, unbroken timeline that stretches back far before the hot, dense state we identify as our beginning. It challenges our core assumptions about gravity and the universe's expansion, painting a picture of a much older and more balanced cosmos where antimatter wasn't destroyed, but simply pushed to the cosmic outskirts. So if antimatter is out there, repelled by our own galactic neighborhood, it would remain virtually invisible to our telescopes, a ghostly counterpart to everything we see. This idea of a hidden cosmic partner compels us to consider an even stranger possibility, one where an entire mirror universe unfolded with time flowing in the opposite direction. Time itself might run in reverse on the other side of the Big Bang. The eighth theory, the Antipodal Universe, proposes that our cosmic beginning was not a wall but a mirror. Imagine the singularity not as a point of infinite density, but as a cosmic fulcrum, perfectly balancing two identical yet opposite realities. On our side, the universe expands forward in time from that event. On the other side, another universe expands away from the same point, but with its arrow of time pointing backward relative to our own. From our perspective, that twin cosmos would appear to be contracting toward the Big Bang, its history unfolding in reverse. A cup of coffee in that universe would, from our viewpoint, assemble itself from spilled droplets on the table, leap back into the cup, and grow steadily hotter. This isn't mere science fiction, but a serious proposal that emerges when we apply the laws of quantum mechanics and general relativity with perfect symmetry. The singularity becomes a bridge connecting two halves of a single, self-contained cosmos. This model offers a profound elegance, solving the puzzle of the universe's initial conditions by making them not initial at all. The state of the universe at the Big Bang doesn't need a special explanation because it is simply the natural, seamless connection point between two temporal mirrors. Physical laws apply identically on both sides, preserving causality within each universe even as they move in opposite temporal directions. This means the question of what existed before the Big Bang gets a stunningly simple answer: another after. The before is just the temporal continuation of our twin universe, forever linked to us through the fiery birth we both share. Could there be a civilization in that other realm, looking back toward the same cosmic event and wondering about the strange, time-reversed universe on the other side? This idea stretches our concept of time to its breaking point and pushes us to contemplate a reality woven from more than the three dimensions we experience. Our cosmos might be a single page in a vast, multidimensional book. This is the core of Brane Cosmology, a theory that reimagines the Big Bang not as an explosion from a point, but as a shattering collision in a higher dimensional reality. According to this idea, our entire three-dimensional universe is a membrane or brane, one of many floating in an unseen expanse often called the bulk. We are confined to our brain, unable to perceive these other dimensions directly, but their existence could hold the key to our origin. The Ekpyrotic model, developed by physicists like Paul Steinhardt and Neil Turok, gives this concept a dramatic, cyclical life. It proposes that our Big Bang was the moment our brain violently collided with another parallel world. The immense kinetic energy of that impact was instantly converted into the searing heat and dense matter that filled our newborn cosmos. Imagine two sheets of paper floating parallel in a silent room, slowly drifting toward one another until they finally smack together. That moment of contact, that cosmic thunderclap, is what we now call the beginning of time. This process is cyclical. After the collision, the brains move apart, their energy spent in creating a new universe. They then slowly drift back together over eons, drawn by a faint force across the bulk, setting the stage for the next great collision and the next cosmic rebirth. This elegant scenario completely avoids the problem of a singularity. There is no point of infinite density, only a transfer of energy between two physical objects in a larger space. It also provides a natural explanation for why our universe is so remarkably uniform and flat. The long, slow approach of the brains before the collision acts like a cosmic eraser, smoothing out any wrinkles or irregularities, preparing a perfectly flat and homogeneous canvas for the new universe to unfold upon. So, what existed before our Big Bang? It was a cold, dark, and nearly empty phase, a long stretch of time where our brain and its twin were silently converging across a hidden dimension. The Bang was not a beginning of everything, but a transformative event, a rebirth from a prior state of existence. This vision of a multidimensional reality challenges us to think of our universe as just one layer of a far grander structure, a concept that finds a strange resonance in the idea that all of this complexity might be built from something as simple as information. Space-time itself may be a frozen artifact of a more fundamental reality. The quantum gravity model dares to suggest that the smooth, continuous fabric of our universe is an illusion, a low-energy mirage emerging from a vast, shifting network of relationships. Picture an immense, abstract web where each point is a fundamental node of reality, and the links between them represent proximity and interaction. In this theory, the pre-Big Bang cosmos was in a state of extreme heat and chaos, a frenzied soup where these connections were constantly forming and breaking at random. There was no consistent notion of time or distance, just a seething, disordered graph of pure information. The Big Bang, then, was not an explosion in space, but a cosmic freeze. As this network of nodes rapidly cooled, it underwent a dramatic phase transition, much like water crystallizing into ice. The random, ever-changing connections suddenly locked into a stable, orderly pattern. This newly rigid structure is what we now perceive as the four-dimensional spacetime continuum, with its three familiar dimensions of space and one of time. The laws of physics as we know them, from gravity to electromagnetism, are not fundamental decrees but emergent properties of this specific, frozen graph. They are the natural rules that govern vibrations and interactions within this crystalline lattice. This implies a staggering possibility that other universes, born from different cooling processes, could have frozen into entirely different graphs, yielding completely alien laws of physics where our concepts of cause and effect might not even apply. Could the very stage upon which our reality plays out be a frozen accident, one specific configuration out of a near infinite number of possibilities? This radical reimagining of space and time compels us to look back to a much older, almost mythological idea of cosmic origins, the concept of a primordial cosmic egg. The fabric of our cosmos might be woven from the gravitational graves of other worlds. The 11th theory, the primordial black hole hypothesis, suggests our entire universe is the interior of a black hole that formed within a much larger parent cosmos. Imagine a massive star in that other universe reaching the end of its life and collapsing inward, its matter crushed into an unfathomably dense point. According to this idea, that point of no return, the singularity, did not mark a final end. Instead, it acted as a cosmic seed, triggering a new Big Bang and birthing an entirely separate spacetime continuum, our own home. The mathematics that describe the event horizon of a black hole, the boundary from which nothing can escape, bear a remarkable and suggestive resemblance to the equations that model an expanding universe like ours. It is as if we are living on the inside of a colossal event horizon, looking out at a reality that is forever cut off from its parent. This concept is powerfully supported by ideas like the Holographic Principle, which posits that the information for a three-dimensional space can be encoded on a two-dimensional boundary, much like the information for everything inside a black hole might be stored on its surface. If this is true, then every black hole that forms in our universe could itself contain a nascent cosmos, a brand new universe with its own unique laws of physics, beginning its own story. This creates a breathtaking fractal multiverse, an infinite cascade of universes within universes, each born from the gravitational collapse of a star in its parent realm. Theorist Lee Smolin took this a step further, proposing a form of cosmic natural selection. Universes that have physical laws conducive to forming many black holes would become prolific parents, giving birth to more offspring universes. Over countless generations, the multiverse would become dominated by universes fine-tuned for black hole production, which, perhaps not coincidentally, are also the universes capable of forging stars and planets. This offers a compelling, non-teleological explanation for why our universe's constants seem so perfectly set for our existence. We may not be in a special universe, but simply in a fertile one, part of an immense, self-replicating cosmic tree. Are we, and everything we see, simply the interior of a black hole in a universe we can never know? This idea of a timeless origin point leads us to a theory that erases the concept of before entirely. Time may be the most persistent illusion of all. The 12th theory proposes that our universe did not emerge into time, but that time itself emerged with our universe, crystallizing from a more fundamental, timeless quantum realm. Before what we call the Big Bang, reality was not a void waiting to be filled, nor a prior cosmos in a linear sequence. It was a state of pure potential described by a quantum wave function, a mathematical expression of all possible configurations of a universe, all existing at once in a superposition. In this state, there was no before or after, no clear sequence of events, only a fog of probabilities. the concepts of cause and effect, so fundamental to our experience, simply did not apply. The Big Bang, in this radical view, was the moment of decoherence. It was the cosmic equivalent of opening the box and looking at the famous Schrödinger's cat. The wave function, which contained all possible universes, collapsed. One specific possibility was selected from the infinite menu, and that single, definite history blossomed into the classical, four-dimensional spacetime we inhabit, complete with its unidirectional arrow of time. This approach draws deeply from the many worlds interpretation of quantum mechanics, suggesting a profound implication. Our entire timeline, from the first star to this very moment, might be just one branch of a vast, eternally splitting quantum multiverse. At the moment of decoherence, every other possible outcome defined by that initial wave function also became real, each birthing its own separate universe with its own unique history and physical laws. We simply ended up on this particular branch. This challenges the very core of causality. If there is no time before the Big Bang, then the universe was not caused by anything in a conventional sense. It simply was a quantum fluctuation that achieved classical permanence. It even raises the bizarre question of the role of an observer. In quantum theory, observation defines reality, but who or what could have been there to observe the birth of everything? The answer might be that the universe observed itself, its own rapid expansion acting as the measurement that collapsed its fuzzy, timeless state into the sharp reality we know. What if the relentless flow of time is just a side effect of quantum processes on a cosmic scale? This vision of a timeless origin compels us to look at a theory suggesting a very different and far more classical precursor. Before the hot fire of the Big Bang, our universe may have been born from a deep cosmic chill. The 13th theory, pre-Big Bang superinflation, reimagines our origin not with a bang, but with a silent, unstoppable stretch. Within the framework of string theory, this model proposes that our cosmos began in a cold, nearly empty state, a vast and quiet expanse where the fundamental strings of reality were placid and undisturbed. Then a shift occurred in the fields governing these strings, triggering a phase of unimaginably rapid expansion known as superinflation. This was not the Big Bang itself, but the dramatic prelude that made it possible. The universe did not explode from a point of infinite density, but instead swelled at an exponential rate from a more manageable, finite beginning. This tremendous stretching did the crucial work of smoothing and flattening the cosmos, creating the perfectly homogeneous and isotropic conditions that the subsequent hot Big Bang would require. Theorists like Gabriel Veneziano developed this scenario precisely to sidestep the troubling singularity, replacing a mathematical breakdown with a smooth, physical transition from a pre-Bang era. In this view, the seeds for everything we see, the faint ripples that would later condense into galaxies and clusters, were imprinted during this superinflationary period. These primordial wrinkles were then amplified and set as the cosmic microwave background, the oldest light in the universe, providing a potential observational link to this cold, pre-birth phase. This elegant idea uses the fundamental tools of string theory to answer a profound question: how did inflation itself begin? It posits that the universe prepared its own stage, setting the conditions for the fiery drama to follow. Such a meticulously structured origin story naturally leads us to ponder an even more radical possibility: that our entire cosmic history is not a product of nature, but of design, running on a computer of unimaginable power. Our universe could be a digital ghost, a flickering reality running on hardware built in a world beyond our own. This is the simulation hypothesis, a theory that dares to suggest our cosmos is not the base level of existence. In this view, the Big Bang was not a physical explosion, but the moment a program was booted up. It was the initialization sequence for an unimaginably complex computational simulation, setting the initial conditions and loading the fundamental laws of physics, which are nothing more than the underlying algorithms of the code. What we perceive as the pre-Big Bang state, that mysterious nothingness, could simply be the hardware or the raw code of a higher dimensional reality running our cosmic program. The question of what existed before our beginning transforms into a question of who or what built the computer. This idea, while deeply philosophical, finds a strange resonance in modern physics. Information theory tells us that the behavior of matter and energy can be described in terms of bits and computations. The Anthropic Principle, which notes how perfectly tuned our universe is for life, could be explained not by divine design or multiversal luck, but by the intentions of the programmers. If a future civilization were to achieve a level of technological maturity, creating hyper-realistic simulations of entire universes might be a trivial exercise for them. If that is the case, then statistically, it is far more likely that we are living inside one of the countless simulations rather than in the one unique base reality. This reframes every mystery of cosmology. The search for a theory of everything becomes the search for the source code. The Planck length, the smallest possible unit of space, might be the pixel size of our reality. Even glitches in the matrix, potential anomalies in our physical laws, could be seen as tiny bugs in the program. Are the constants of nature fixed, or are they simply variables set by a developer at the start of the runtime? This provocative idea pushes our understanding of reality to its absolute limit, forcing us to confront the possibility that our quest for a beginning is merely a search for the login screen of a reality we can never truly leave. Such a profound reliance on the concept of a foundational nothing from which everything emerged leads us to the final and perhaps most elegant theory of all, one that finds genesis in the quiet hum of empty space. Even the deepest void is not truly empty. The quantum vacuum fluctuation theory asks us to see the nothingness that might have preceded our universe not as a sterile emptiness, but as a vibrant, seething sea of potential. This quantum vacuum is a realm where the laws of physics permit a bizarre but fundamental phenomenon, the spontaneous, temporary appearance of particle-antiparticle pairs from pure energy, only for them to annihilate an instant later. These are virtual particles borrowing energy from the void for a fleeting moment before repaying the debt. The theory proposes that our entire cosmos is the ultimate example of this process, a fluctuation that did not vanish. In this model, our universe is a quantum bubble that formed spontaneously in a pre-existing metastable vacuum, a random event on a cosmic scale. It tunneled into existence through a process called quantum tunneling, where a system bypasses an energy barrier it classically shouldn't be able to cross, much like a ball appearing on the other side of a hill without ever rolling over the top. The mathematical framework for this, involving tools like the Wheeler-DeWitt equation, describes a universe popping into being from a state of nothing, with its entire history unfolding from that single, uncaused event. Physicists like Alexander Vilenkin have championed this view, suggesting the quantum vacuum is eternal and universally fertile, capable of giving birth to an endless array of disconnected universes, each a random fluctuation in an infinite, timeless sea. This offers a profoundly minimalist explanation, one that requires no prior cosmos, no colliding brains, and no intelligent designer, only the established, if strange, rules of quantum mechanics stretched to their ultimate limit. It presents our existence as the ultimate free lunch, a cosmic accident of staggering proportions. Could everything we hold as real, from the grandest galaxy to the most fleeting thought, be the result of a single, random tick in the fabric of nothingness? As we stand at the edge of this vast mystery, looking back over these 15 incredible theories, we are left not with a single answer, but with a breathtaking spectrum of possibilities. From cyclic eons to holographic projections, from bouncing universes to simulated realities, each idea challenges our most basic assumptions about time, existence, and our own place in the cosmos. They are not mere speculation, but the leading edges of human reason pushing against the ultimate veil. The true wonder lies not in which one is correct, but in our relentless drive to ask the question at all, to peer into the abyss before the dawn of time and dare to imagine what we might find there. We have traveled across the landscape of human imagination, from universes that breathe in eternal cycles to cosmic projections on a two-dimensional screen. Each of these 15 theories, from the quantum bounce to the simulated reality, represents a different path through the same fundamental mystery. They are not just wild guesses, but rigorous frameworks built upon the bedrock of mathematics and quantum principles, each one a testament to our species' relentless drive to look beyond the horizon of the known. The fact that we can even formulate such profound questions about the moment before time is a triumph of the human spirit. While we may not yet have a definitive answer, the value of this quest lies not in a final destination, but in the journey itself. It forces us to refine our laws of physics, to build better telescopes, and to question the very nature of reality. This exploration is a celebration of curiosity, a reminder that the universe's greatest wonders are often hidden in the questions we have not yet learned to fully ask. If this journey through cosmic origins has ignited a sense of wonder in you, we would love to hear which theory resonates most deeply with your own view of reality. Share your thoughts in the comments below, and if you are eager for more journeys to the edge of understanding, be sure to subscribe. Thank you for contemplating the greatest of all mysteries with us, the enigma of what, if anything, came before the dawn of everything.